So we're talking about Lewis theory, and we've gone over how to write Lewis structures, and we've covered the octet rule. So, of course, there have to be exceptions to rules, right? So there are molecules that have an odd number of electrons. If you have an odd number of electrons, it's not possible to make a Lewis structure where all of the atoms have octets. These sorts of molecules and ions are called free radicals. So they have an odd number of electrons. They tend to be unstable and very reactive. You guys heard of free radicals? Are they good for you? No, you want to minimize the free radicals in your body because free radicals are reactive and they tend to react with things maybe in ways that would not be beneficial to you. They're unstable. So let's look at the structure for one of my favorite molecules, nitrogen monoxide, which I think of as no. So we have a nitrogen and an oxygen. And we've got a total of 5 plus 6 electrons, right? 5 from the nitrogen, 6 from the oxygen, so that's 11. So that's an odd number. We can tell we're going to have a problem here. Well, we're just going to do the best we can. So we'll put a bond in there. Nope, not like that. Put a bond in there. That's 2 electrons. And there's 4, 6, 8, 10, and 11. So then we evaluate what we've got there, and the nitrogen has 7 electrons. The oxygen only has 6. So what we want to do is take a pair of electrons from the atom that has more and share it. So we'll take a pair of electrons from the nitrogen and make that into a double bond. And then we see what we've got. Now the oxygen has an octet, but the nitrogen still has 7. So we could evaluate the formal charges. So what's the formal charge on that nitrogen? It brings in 5 electrons, right? And how many does it take? 5? So that has a formal charge of 0. Right? Because formal charges, we imagine breaking these bonds in half, and there's 4 electrons here in the middle. 2 go to the nitrogen, 2 go to the oxygen. Right? So the nitrogen would leave with this one, 1, 2, 3, 4, 5. Nod your head if you are okay with that. Shake your head if you're not okay with that. Okay. Oh, yeah, if you missed the last lecture, that would be a problem. Well, there's probably at least one other person that's a little unclear. The way I approach formal charges is we imagine just cutting this in half. Each of these bonds contains 2 electrons. And so for formal charges, we're comparing the valence electrons that the atom brought into the molecule with what it would take if we just cut all the bonds in half. I think of it like, these guys came together and formed a corporation, and this guy contributed $1,000 and this guy contributed $5,000, and then we decide to dissolve the corporation, and so we're just going to cut everything in half and see what people end up with. Some people are going to come out ahead, some people are going to break even, some people might take a loss. So in this situation, nitrogen brought in 5 electrons, and it would leave with 5 electrons, and so that's breaking even, a 0 formal charge. That's a good thing. And then if we look at the oxygen brings 6 electrons, because that's how many valence electrons it has, and when it leaves, it's going to take its lone pairs, 2 and 4, and these 2 bonding electrons, so it's going to have 6. And so that's going to be 0 formal charge. So the nitrogen does not have an octet, but we've got 0 formal charges, and so that might be the best we can do. Any questions? We can't go more than 8 electrons, because these guys can't do that. So nitrogen monoxide does exist, especially in air pollution, but then it tends to react with things and form other compounds. So the Lewis model can't handle everything. It's a very simple model. So we just write the best Lewis structure that we can, and just call it good. It's the best we can do. So that's one way you can violate the octet rule. Another way is to have an incomplete octet. So we know that hydrogen and helium are only going to have 2 electrons in a compound because they're very small. There are some other elements that will also form incomplete octets. Hydrogen and helium follow their own special rule called the duet rule, but these other elements are kind of stuck in the middle. They're bigger than hydrogen and helium, but smaller than the rest of the elements, and so they kind of, they can vary. Sometimes they'll have 8, and sometimes they'll only have 6. So boron is one of those. It tends to form compounds in which it has 6 electrons instead of 8. So let's draw the Lewis structure for boron trifluoride. So the boron's going to be in the middle, and the fluorines are going to be bonded to it. That arrangement is suggested by the fact that more electronegative elements tend to be terminal. And then we need to count up the number of electrons. How many valence electrons does boron have? 3. And how about those fluorines? 7. So there's 3 of them, and they each have 7. So that's 21 plus 3 is 24 electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So when I put 24 electrons around like that, the fluorines all have octets. The boron does not. And so we might be tempted to take a lone pair from one of the fluorines and make a double bond so that boron can have an octet. But let's look at the formal charges first. So on those nitrogen atoms, each nitrogen atom brought 7 electrons to the molecule, valence electrons. And when we cut the bonds in half, how many will it leave with? 7. So that has a 0 formal charge. All the fluorines are going to be the same, right? Because they all have 1 bond. And then let's look at the boron. The boron brought 3 electrons. And bless you, if we cut all these in half, how many does boron leave with? 3. So it also has a 0 formal charge, even though it does not have an octet. So this is violating the octet rule, but it's a stable molecule, and this is what it does. It does not have resonance or any double bonds. This molecule will tend to react in a way that will complete that octet, but it will be fine as it is. Beryllium also tends to have incomplete octets, and beryllium's kind of a funny one because beryllium technically is an alkaline earth metal, right? And so then we don't necessarily expect it to form covalent compounds, and yet it kind of does. So it's those little elements that can violate the octet rule. So we just need to be aware of that. And again, formal charge is the guiding principle of, do we make double bonds to complete the octet or not? Any questions? We can also violate the octet rule in the opposite way by expanding the octet. And this can occur in elements in period 3 and larger. They can expand their octets up to 12 or even 14 electrons instead of 8. So let's look at these 2 compounds, arsenic pentafluoride and sulfur hexafluoride. So the arsenic's going to go in the middle, And then we've got 5 fluorines. And so these are going to go around, and normally we just have top and bottom, right and left, but now we've got a 5th one, so we're going to have to squeeze it in here. Arsenic has 5 valence electrons, and we've got 5 of the fluorines. 5 times 7 is 35, so we've got 40 electrons here. So we've got 2, 4, 6, 8, 10 in the bonds, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. If we look at their formal charges, fluorine brings 7 electrons and it leaves with 7, so it has a 0 formal charge. The arsenic was bringing 5 valence electrons in, and if we cut all those bonds in half, it will also leave with 5 electrons and have a 0 formal charge. You could draw other structures that don't violate the octet rule. Well, actually, maybe you couldn't. There's just too many electrons. You could try putting this fluorine off of another fluorine so that you only have 8 around arsenic, but you're not going to be able to do anything else that gives you 0 formal charges on everything. Sulfur hexafluoride is going to be a similar thing. Put sulfur in the middle and the fluorines around it. So there's 6 fluorines. This is not the way I teach you to draw Lewis structures, but it's another method that works. Each of these fluorines brings 7 electrons. And so if I just look at that one up in the corner, so there's its 7th electron. It's got 6 in lone pairs, and it's got this 7th electron that's going to make a bond with the sulfur. So that's the correct number of electrons for all the fluorines, and then they're going to have 0 formal charge when they do that. And then the sulfur brought in 6 electrons. 1, 2, 3, 4, 5, 6. And so if it makes 6 bonds, and we break all those bonds in half, it would also leave with 6 electrons, and then it would have a 0 formal charge. That make sense? So these are both stable compounds. And the reason they can do this is because in period 3, 4, 5, 6, etc., we have d orbitals that are available. They're higher in energy than the s and the p orbitals, but not that much. They're energetically accessible, and so we can expand into those d orbitals and make more than 4 bonds. And we'll see more clearly how that works when we talk about valence bond theory. Any questions? So, could nitrogen ever do this? What period is nitrogen in? Period 2? So, nitrogen has an electron configuration that ends in 2s2, 2p3. It can't expand into the d orbitals because there are no 2d orbitals. So it can't. So those period 2 elements, nitrogen, carbon, oxygen, fluorine, they cannot expand their octets. But the ones below them in the periodic table can. Let's look at another example. Sulfuric acid, H2SO4. So this is one of those oxyacids. And with the oxyacids, the oxygens are bonded to whatever nonmetal is present, and then the hydrogens are always bonded to the oxygens. So the sulfur's going to be in the middle. Wrong marker. And then we're going to have oxygens around it. And the hydrogens will be attached to oxygens. So counting up electrons, the sulfur has 6, and there's 4 oxygens. They each have 6 electrons, and 2 hydrogens, each with 1 valence electron. So that's what, 32? So if we count the bonds first, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, come on, 30, 32. That looks good, right? Everybody's got an octet. Let's look at the formal charges. Hydrogen always has a formal charge of 0. What's the formal charge on this oxygen? Six minus 6, 0. This one's going to be the same because it's the same arrangement. It has 2 lone pairs and 2 bonds. Anytime oxygen has 2 lone pairs and 2 bonds, it's going to have 0 formal charge. This oxygen's a little different though. This has 3 lone pairs and 1 bond. And so it's still brought in 6 electrons, but when it leaves, it's going to have 7. So this is going to have a -1 formal charge. And the oxygen down here is going to have a -1 formal charge. And then let's check out the sulfur in the middle. Sulfur brought in 6 electrons, and it would leave with 4. So it's going to have a +2 formal charge. So that structure looks great because it fits the octet rule, but the formal charges aren't so awesome. So we can draw that differently by expanding the octet on that sulfur. So if we put the sulfur in the middle, this -1 formal charge tells me that this oxygen maybe has too many electrons, and the +2 charge on the sulfur says the sulfur doesn't have enough. So we can expand the octet of the sulfur by taking one of these lone pairs from this oxygen and making a double bond. So I'm going to make a double bond here. I'm going to stick the rest of the electrons in there. So now this oxygen has 2 lone pairs and 2 bonds. It's a double bond, but it's still 2 bonds. And you can count up the electrons, and that oxygen now has a 0 formal charge. This one down here, of course, we haven't changed, so it's still -1. And if you look at the formal charge on the sulfur now, what is it? The formal charge is +1. Okay. So we're going to cut all these bonds in half, right? So the sulfur is going to get 1, 2, 3, 4, 5 electrons. It'll leave with. It brought 6 in. 6 minus 5 is 1. So this has a formal charge of +1. That's better, isn't it? But we could make them all 0 If we did a similar thing with this oxygen, took a lone pair from this oxygen and made a double bond. So take a lone pair from that oxygen and make it a bond. Now when we look at this oxygen, it's going to have a 0 formal charge. And the sulfur is also going to have a 0 formal charge. Because sulfur brought in 6 electrons and it's going to leave with 6. 1, 2, 3, 4, 5, 6. This violates the octet rule, but sulfur's a big boy and can do that. Expand into the d orbitals. So this is the actual structure, and Lewis theory helps us to predict this versus this first one by looking at the formal charges. Any questions? Just remember, period 2 elements never have expanded octets. It's just not possible. So here we're talking about expanded octets. These are a lot of the structures that show up on worksheet 9 that we did last week involve these expanded octets. So let's write the Lewis structure for XeF4, xenon tetrafluoride. So we'll put the xenon in the middle and fluorines attached to it. Then we have to count up electrons. How many valence electrons does xenon have? 8. And I have 4 fluorines, and they each have 7. So that's 21. No, that's 28 plus 8 is 36. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've given everyone an octet, and I've only used up 32 electrons. I've got 4 more electrons. Where are they going to go? They're going to have to go on the xenon, right? So this is different than the problem we had earlier where we didn't have enough electrons, so we had to make multiple bonds. Here we've got too many electrons for octets. The only element here, the only atom that can expand its octet is xenon. The fluorines can't because they're too small. So we'll just stick those two, stick 2 lone pairs on the xenon, and that takes care of our extra 4 electrons. What are the formal charges? So in case you've forgotten, for those main group elements, when we look at the Lewis structure for the atom, we see that fluorine has 7 valence electrons. That leaves 1 of them unpaired. And the way that works out is if fluorine forms 1 bond, then it'll have 0 formal charge. So that can save us a lot of counting. So we can look at these fluorines, they all have octets. 1 bond, they're all going to be 0. So we need to check out the formal charge on xenon. Xenon brought in 8 valence electrons. And how many would it leave with when we cut those bonds? 8. So we leave with 8. And so we've got 0 formal charges. Any questions? So let's do phosphoric acid. Again, this is an oxyacid. So the phosphorus will be the central atom. The oxygens will be attached to that. And the hydrogens are attached to the oxygens. Okay, so we've got the skeleton there, and we have to count up the number of electrons. 3 hydrogens, each with 1 valence electron. We have 1 phosphorus that has, how many? What group is it in? 5. The phosphorus has 5. We have 4 oxygens. How many valence electrons does an oxygen have? 6. There is no shame in doing this sort of math on a calculator. You know, our brains just skip sometimes. I'm going to try to do this in my head. So 24 and 8 should be 32. Because it's a shame to do all this work and get it wrong because you add it in your head. Okay, so we got 2, 4, 6, 8, 10, let's see, I lost count. 2, 4, 6, 8, 10, 12, 14. So we'll keep counting. 16, 18, 20, 22, 24, 26, 28, 30, 32. So I put all my electrons around, and I got octets on everybody. Well, let's remember what oxygen has a Lewis structure that looks like this. So when oxygen forms 2 bonds, it's going to have a 0 formal charge. Do all of those oxygens have 2 bonds? No. Thinking of it this way is sort of a shortcut to save you a lot of counting and subtracting. So I can look at this one. This oxygen brought in 6 valence electrons. It would leave with 2, 4, 5, 6, 0 formal charge, 0 formal charge, 0 formal charge. This one has a formal charge. It brought 6, it's leaving with 7, so it has a -1 formal charge. What's the formal charge on that phosphorus? +1. So the phosphorus brought in 5 electrons, and it's leaving with 4, so that's +1. Can phosphorus expand its octet? Yes. It's in period 3. It can do that. So what we can do is expand the octet and take a lone pair from this oxygen who has a little too many electrons and share with this phosphorus that doesn't quite have enough. So we'll take that one off and make it a double bond. And now if we address formal charges, the oxygen brought in 6, 2, 4, 5, 6. It would leave with 6. So this has a 0 formal charge. Phosphorus brought 5 electrons in, and now it would leave with 5 and also have a 0 formal charge. Any questions?